We started surface parameterization. We saw different examples. We solved the disk parameterization, the cylinder parameterization, and the cone parameterization. So now let's continue with this theme. So in this example, we want to see how to parameterize a sphere. So let's give this example this title: Sphere Parameterization. And it's enough to discuss the unit sphere. So what do we mean by the unit sphere? We just mean x squared plus y squared plus z squared equals 1. Of course, in general, if the radius is r, it's x squared plus y squared plus z squared equals r squared. Of course, here the center is the origin. So we are talking about this sphere like this. And this is the origin. Now the idea, recall from Calculus 3, we had some hints in Calculus 3, especially when we treated the double and triple integrals. We know from Calculus 3 that usually polar coordinates are best with circular regions. Cylindrical coordinates are best with cylindrical region. And spherical coordinates are best with spherical regions. So before doing the sphere parameterization, we need to revise the spherical coordinates. So this is how we will parameterize the sphere. So what do we mean by the spherical coordinates? Take any point P, X, Y, Z. So we have a point called P. The coordinates are X, Y, Z. Of course, this point is in R3. So imagine X, Y, Z, and we have some point anywhere. It could be here. So this is my point, X, Y, Z. Okay? Okay. Now, the first thing, let's denote the square root of x squared plus y squared plus z squared. So what is this? This is the distance from the point P. Please, we need to distinguish between the point P and rho. So the point P, which is the x, y, z, and the origin. So if we look at our figure, this is the origin, this is the point P, this is the distance rho. So this is what we mean by rho. So we just measure the distance from the point to the origin. This is the first thing. And this will be the first spherical coordinate. Then let theta be as usual. So what do we mean by theta? We are used to deal with theta in the two-dimensional case with x and y only in R2. But we can have theta for points in R3 as follows. So the idea, what do we mean by as usual? We project the point P, X, Y, Z onto the X, Y plane. Then we find the angle, find theta with the positive x-axis. So what do we mean by this? We mean, okay, so this is my point. Take it down to the xy plane. So this point will be x, y, 0. Now this point, it has a certain theta with the positive x-axis. So this is what we mean by theta. So this will be exactly like theta, the one we know from Calculus 3 or Calculus 2. So this is the x-axis, this is the y-axis. Basically, we have x and y if we take just the xy plane. So this is my point, and this is theta. So we know we know the formulas. So here we know that x equals r cosine theta and y equals r sine theta. What is r? R is this distance, which is exactly this distance here. So this distance here, it is the r value. Not only this. In fact, so this is the theta. So now what is r? What is r? Now I don't want to see the r. So the spherical coordinates, r is used when we deal with cylindrical coordinates. If you're dealing with spherical coordinates, you will have the rho, you will have the theta, but not the r. However, for the r, we need to add one more parameter. So the third parameter, which will help us find r, is, so let phi be the smaller angle between P with arrow and the positive Z axis. So what is phi? If you look back at our figure, so this is what we mean by P, the arrow P. This is P arrow. Remember, if you have a point P and you add the arrow, that means the vector from the origin to that point. Now we are measuring the angle between the vector P and the positive Z axis. So this is my phi. Okay? Okay. Now what is this point here? What is this point here? This point here, if we change the color, this point here is, you are taking x as 0, y is 0, but you are keeping the z. So basically, if you find the distance between this point, we need more colors. If you find the distance between this point and this point, so you are taking x minus 0 square, y minus 0 square, z minus z square. So basically, this is the distance is the square root of x square plus y square, and that's exactly r. Remember, if you look at this r from r2, this r is root x square plus y square. Okay? So now, if you look at phi, what is then sine phi? Sine phi, this is phi, this is my triangle. So sine phi is the opposite over the hypotenuse, but the opposite is r. This is phi, that's the opposite. So it's r over, what is the hypotenuse of this triangle? It is rho. So basically r is, and this is what we were looking for, we wanted to find r, it's rho sine phi. On the other hand, if you look at cosine phi, what is cosine phi? This is phi again, and this is the adjacent, right? This is here the adjacent, and what is this? This is exactly z. So cosine phi is z over rho, which means z is rho cosine phi. So now going back to the x and y formulas in terms of r and theta, so now my summary is, so given P, my point, x, y, z in R3, we have the new coordinates. In order, we write rho, theta, phi, where what is rho is the root of x square plus y square plus z square. What is theta? Theta is found from this formula. We'll write the formula. And what is phi? Phi is cosine inverse from this line. Phi is cosine inverse z over rho. And we need here to mention that in general, if cosine phi is z over rho, does it mean that phi equals cosine inverse? Yes, yes. If phi is between 0 and pi, and this is guaranteed because we are dealing with the smaller angle, and we will discuss in minutes what we mean by the smaller angle. So what about theta? Theta, we have x equals, we have y equals. So if we look back at the xy plane, so this is my point xy, and this is theta. We know that x is r cosine theta, y is r sine theta. So basically, if you divide tan theta is y over x. However, because theta is ranging from 0 to 2 pi, we can't just say theta is tan inverse y over x. So basically, what is the exact formula for theta? Okay, it is tan inverse y over x if x is positive. And please remember, why is this restriction? Because the tan inverse gives you values only from negative pi over 2 to pi over 2. When you say negative pi over 2 to pi over 2, this is here the negative pi over 2, this is the pi over 2, which means you are covering this region. So now if you use your calculator and find tan inverse of anything, any value, you will never get anything in the second quadrant or the third quadrant. You will just get something in the fourth quadrant and the first quadrant. That's why the tan inverse from this formula, it is true only if x was positive. This is the right half plane. So what about if your point is in the second or the third quadrant? You add pi, so it's pi plus tan inverse y over x when x is negative. Of course, what happens when x is 0? When x is 0, that means your point is either on the positive y-axis or the negative y-axis. If it's on the positive y-axis, the angle is pi over 2. If it is on the negative, the angle is negative pi over 2. So these are together. So these are the so-called spherical coordinates. Okay, before we continue, let's just emphasize the meaning of the smaller angle. So remember, when we talked about phi, we said it is the smaller angle between the vector p and the positive z-axis. So let's just talk a little about phi. So the idea, if you take any point on the positive z-axis, what is phi? Phi, again, it is the angle made between the positive z-axis and the vector from the origin to the point. So now if your point is already on the positive z-axis, the phi would be 0. If, for example, you take any point on the positive x-axis, so again, if this is your point, you measure the angle between this arrow here, you measure the angle between this arrow and the positive z-axis, and in this case, the phi would be pi over 2. Now imagine you are going to the negative z-axis. So this is the negative z-axis. If you take any point on that negative z-axis, so you draw the vector from the origin to that point, what is the angle? What is the angle with the positive z-axis? It is pi, exactly. Now let's go a little beyond that. So if you take a point here, if this is your point, and this is your vector with the positive, with the origin, then when you talk about the angle with the positive z-axis, you can talk about this or that one. You have two angles to measure with the positive z-axis. And now it is clear that this is the smaller angle. So this is my phi, not this. So this is the meaning. This is the meaning of the smaller angle. And because of it, the fact that it is the smaller angle, it's always between 0 and pi. And again, let's, before seeing the sphere parameterization quickly, so let's see, for example, the graph. So sketch the spherical equations, just to make sure that we understand the meaning of spherical coordinates. let's see some equations in terms of rho, theta, and phi. But please, we need to remember the meaning of every single one. So what is the meaning of rho? It's the distance from P to the origin. What's the meaning of theta? What's the meaning of phi? So for example, if rho equals 2, what is that? Because the rho is the distance, so that means when we say sketch, that means we are looking for all points that satisfy this equation. So basically, we want all points which are 2 units distant from the origin. So imagine you draw the axes x, y, z, and you are looking for all points whose distance from the origin is 2. So you move in this direction 2 units, 2 units, 2 units, 2 units. But because you are in R3, you can go everywhere in the space. And if you agree, this is exactly a sphere. So this will be a sphere centered at the origin with radius what? With radius equals to 2. So in general, if you take rho equals a fixed value rho node, this is a sphere. So this is the graph of the spherical equation rho equals any number. Now what about if we take theta, for example, theta equals 0. So we want to sketch all points in R3 whose theta is 0. So now we need to look at the meaning. What do you mean by theta? Theta, again, theta is always taken from the xy plane. So now I want to draw, this is the xy plane. What do we mean in the xy plane by theta equals 0? Theta equals 0 means all points here on the positive x-axis. But this is not what we want. This is in R2, and we are talking about a sketch, a graph in R3. So now we go to R3. This is x, y, z. I know that in R2, this is my theta equals 0. But because, if you remember, how did we find the theta? We said project the point onto the xy plane. So the idea, when we're dealing with points in R3, if you want their thetas, take it, project it down to the xy plane. All these projections have the same theta. So if you take any point above the x-axis like this, this point, all of them, when you project them down to the xy plane, you will have something on the positive x-axis. That means their theta is 0. So this is the graph of theta equals to 0. So let's call this is, if you agree, it's a half plane attached to the z-axis. This is a half a plane. So this is how we draw theta equals to 0. For example, if we want to draw theta equals to pi over 4, again, you look at it in R2, this is xy, you make an angle of pi over 4, but when you move to R3, x, y, z, you draw the angle pi over 4. Then you say, okay, all points that are above this line, all of them, they have exactly the same theta. So again, this is a plane attached to the z-axis. So now we can imagine how the thetas are drawn. So you just draw this line segment in R2, then extend it in the direction of the z-axis. Now let's see the phi. Okay, so let's draw phi equals 0, phi equals pi over 2, phi equals pi over 4, phi equals pi, phi equals, for example, 2 pi over 3. Just to make sure we understand exactly what we mean by the smaller angle, because this makes a big difference. So we are dealing with R3. This is x, y, z again and again. What do we mean by phi equals 0? Phi equals 0 means I want to figure out all points whose vectors make the angle 0 with the positive z-axis. This is the positive z-axis. So I want all points that when we draw their vectors to the origin, they make the angle 0 with the positive z-axis. So that means basically it is the positive z-axis because the angle is 0. That's it. So phi equals 0 gives you the positive z-axis. What do we mean by theta equals pi over 2? Phi equals pi over 2 means we need all points. For example, this point. So when you draw the vector to the origin, this is the P arrow. This is the angle pi over 2. So you're making the angle pi over 2 with the positive z-axis. But this is not restricted to the positive x-axis. If you take any point on the positive y-axis, you still have the angle 90 degrees with the positive z-axis. Again, it's not restricted to that. In fact, if you take any vector on the xy plane, it will make the angle pi over 2. So basically, phi equals pi over 2. This gives you the xy plane. If you take any point on the xy plane, you draw that vector to the origin, you will have the angle 90 degrees with the positive z-axis. Now, what about phi equals pi over 4? So we are looking for all points P that when you draw the vector from the origin to the point P, so this is the vector P, the angle with the positive z-axis is pi over 4. But this thing can be done in all directions. And remember, we are dealing with R3, not R2. So we are going in all directions, pi over 4, pi over 4, pi over 4, which means, let's do it separately here, which means basically you're having a cone. So this cone here with angle pi over 4, this is the graph of phi equals pi over 4. What else? Phi equals pi. So if you draw the axis, so now you want your point to have an angle pi with the positive z-axis. So this is the positive z-axis. The angle pi means you are going down to the negative z-axis. So if you take any point here on the negative z-axis, you measure the angle between the positive z-axis and that vector, it will be exactly pi. So basically, phi equals pi, this is the negative z-axis. So this is phi equal pi, it's the negative z-axis. So it remains to sketch phi equals 2 pi over 3. So these are the axes again, sorry. X, y, z. So we need the angle 2 pi over 3, which is 120 degrees. So if you start with the positive z-axis, you reach the xy plane, the angle is 90 degrees. So you need to exceed the xy plane to reach the angle 2 pi over 3. So that means this is, sorry, let's just do it neatly a little bit. Okay, so you need to make the angle, this is the angle 2 pi over 3, this is the angle 2 pi over 3, but this needs to be done in all directions, and if you do it in all directions, you will get a cone, another cone like this. So this is phi equals 2 pi over 3. Again, it is a cone, and this one is a cone. So this is the meaning of phi. So basically, our understanding for phi, phi equals 0 is exactly the positive z-axis. Then, as phi gets increasing, it's like you are separating, you are cutting this yellow array in the middle, and it goes like this. So it gives you a cone. As phi increases, you are getting a larger cone, a larger cone, a larger cone. When you reach pi over 2, you get exactly this cone will be exactly the xy plane. And then as phi increases, this xy plane goes down to this plane. sorry, to this cone, to this cone, to this cone, and these cones keep getting smaller and smaller until you get the negative z-axis when you reach pi. So this is our understanding for the phi values. Okay, so these are the spherical coordinates. Now going back to our, remember, we started our example and we wanted to find the sphere parameterization. So now how do we parameterize the sphere? How do we parameterize the sphere? Okay, so back to sphere parameterization. So if you take any sphere, so I'm talking about a sphere now centered at the origin. So this is the origin. This is the origin. If you take any point on that sphere with radius rho, now we know that any point in R3 can be written as, remember, x is r cosine theta, y is r sine theta, and z is rho cosine phi. This is what we found here. Z is rho cosine phi. But because we don't need the r, so we need to write the r in terms of the new coordinates. Remember, we found it. We found that r is rho sine theta somewhere. This is it. So now we replace r with rho sine phi, and you keep cosine theta. Y is r, again you replace the r with sine phi, rho sine phi, you keep sine theta, and the z is rho cosine phi. So any point in R3, it must have these three coordinates in spherical coordinates. Okay? So now, if you take any point on the sphere, take any point, wherever you like, for sure the rho is fixed. For sure the rho is fixed. But what about the theta and phi? They are changing. The theta has to range from 0 to 2 pi, and the phi from 0 to pi. So basically, I can write my parameterization for the sphere. So any point on the sphere, it will have this parameterization. Rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. And remember, for us, because we are dealing with a sphere, this rho is a fixed value. So for example, if the radius is 1, as in the unit sphere, rho is 1. If it's 2, 2. But the theta and the phi, so the theta is from 0 to 2 pi, and the phi is from 0 to pi. If we want to be more accurate, the theta cannot be 2 pi, so that we have a unique representation for any point. Because if you say theta can be 0 and it can be 2 pi, then you can select for points on the positive z-axis, you can select 0 or 2 pi. To guarantee uniqueness of the coordinates, we just say theta is bigger than or equal to 0 and less than or equal to less than 2 pi without the equality. So now, for example, the unit sphere has the parameterization. So now, what is the radius in the unit sphere? It is equal to 1. So basically, the parameterization for the unit sphere will be, so the rho is 1, you just replace it, and that's it. Now, what about if the radius is 2 or 3 or whatever? That's fine. It's the same idea. But what about, so what happens if the center is not 0, 0, 0? So we want to parameterize. So we want to parameterize x minus, let's say, x naught square plus y minus y naught square plus z minus z naught square equals rho square. The idea, this equation looks exactly like a sphere centered at the origin, but if you replace x, it's like you are replacing x minus x node, you change it to x, y minus y node, you change it to y, z minus z node, you change it to z. So this is like the new x, the new y, the new z. So if you move this there, this there, this there, so basically, so if the radius in general, if the center is x node, y node, z node, and the radius is rho, this is again a fixed value, the parameterization will be r theta phi. It will be exactly like the unit sphere, like this, but we add the coordinates. So it will be x node plus rho sine phi cosine theta, y node plus rho sine phi sine theta, and z node plus rho cosine phi. This will be my parameterization, and again the theta is from 0 to 2 pi, and the phi is from 0 to pi. This is the full details of the sphere parameterization, and this will be very crucial in our understanding of this surface integrals.